Hi, I am Professor Tamal Mandal, Department of Chemical Engineering, National Institute of Technology, Durgapur. Today I am talking on biological reaction engineering, and as the most of the biological reactions are homogeneous in nature, and if in case of any difference in concentration or temperature, then it is called the heterogeneous. And basically the reaction theory has two fundamental parts. One is the reaction thermodynamics and reaction kinetics. So in this case, consider the reversible reaction represented by the following equation, and here the if we take the some species as a reactant, then it reacts and give the products and up to a thermodynamic equilibrium. After that, a dynamic equilibrium is established, same as chemical and biological both the system. And biological reactions basically consider the two types of reaction. One is the enzymatic and another is the microbial reaction system. And this is also follow the similar rule of the chemical reaction engineering, and this the equilibrium constant can be written as a in this equation ln k minus Gibbs free energy terms, and then RT is the R is the ideal gas constant, T is the absolute temperature. So, the delta G is the equal of difference of a standard free energy of formation, and this is nothing but coming from the reactants and products form, and this can be presented in this equation in the enthalpy and entropy form also. And here the from this conversion ultimate this combination equation is presented that the with increasing temperature the rate is going to be reduced, but the second term is helping to make it up, and for the endothermic reaction this part is positive. So, then the this k value is increasing following the Arrhenius equation, and reaction yield is very important, as this is the how much extent of production is forming from a reactants. So, with and reaction rate is another term which is very important for time point of view, that the per unit production taking how much time. So, then we will go for the how we can measure the biological reaction rates similar as the chemical process. Here m is in mass or in micros form, here in T is the time. So, the mass if mi is the mass flow rate, here we can consider the how much mass of microorganism in coming into the system, and m0 is the mass flow rate out of the system, and Rg is the mass rate of generation, this is the microbes how much generating, and Rc is the mass rate of consumption by reaction. So, the total rate is nothing but coming the total production rate of a plant, if any specific examples. So, then volumetric rate is nothing but for designing of any reactor per unit volume how much mass converting to the product, that will be calculated. So, here as per the requirement of product the volume of the reactors can be designed. Although the increasing the volume, it will affect some heat transfer, mass transfer and momentum transfer point of view. Based on that, the if the volume is so high, then the production may be a little bit retarded or may be different from the lower scale operation. But almost that is the only possibility or the only way to scale up of the process from here. And another is the a specific term is the per unit mass of biomass, how much giving the product, that is 1 by x is the biomass concentration and 1 by E is the or on is enzyme concentration. So, using the enzymes how much product we are getting per unit volume of reactor, and similarly for biomass 1 by x into dm A by dt, how much product is forming per unit mass of biomass, specifically microbes. But these also differ from their origin of, suppose the what types of microbes we are using, that maybe their age, their quality also depends. And similarly for enzymes also, different enzymes, the enzymes may be same, but the source may be different, and for this the enzyme activity may be different. So the enzyme activity has to be measured, and then from there only we can consider that the per unit of activity measured under the specified conditions. 1 unit of enzyme is usually taken as the amount which catalyzes conversion of 1 micromole substrate per minute or at the optimal temperature, pH and substrate concentration. That means the process control and the process parameters point of view, that the most suitable condition will be presented for the calculation of the enzyme activity. Then reaction kinetics will be calculated from these biological reactions, and the overall reaction kinetics from the chemical point of view we can present in this equation, but from the biological reactions it is normally come in different way, and the temperature also affect in the chemical kinetics, but at the same time biological reactions also very much affected to the temperature. Not only for the rate constant point of view, but another is the microbial growth point of view, as the microbes are when they are showing their activity, it is the very narrow range of temperature they show their maximum activity. Enzymes also similar way, either if we increase the temperature beyond a certain specific temperature, then the denaturation of the enzymes may occur, and below the temperature of its optimum condition, then the enzyme activity may not be that much, or it is basically reduced the activity. So, the productivity will be hampered. So, the optimum temperature maintain is very much important from the biological reaction point of view, and that from the microbial growth point of view, similar way the temperature effect is very high, that the if the temperature is the microbes is growing at 30 degrees centigrade, and if it is for the reaction kinetics, if we increase it to 35 degrees centigrade, so the microbes may die fully due to the thermal shock, and if it is at the lower temperature, then also similar types of phenomena may occur and the productivity will be hampered. So, we have to maintain the optimum temperature in that specific zone of temperature only. So, zero order kinetics is another important for the biological reactions also. There we see that the substrate concentration is not important, or the reactant concentration, it is independent of reactant concentration, but this K0 value is defined as the above equation. It is the volumetric rate constant as it units kg mole per meter cube per second, but this K0 value also depends on the enzyme concentration or as the microbial concentration how much present there. So, this can be written in the for the biological reaction K0 equals to K0 prime and into E is the enzyme here, or K0 into K0 double prime into X is the microbial concentration here. X is the microbial concentration here. Here K0 is the specific zero order rate constant for the enzyme reaction and E is the concentration of the enzyme. Correspondingly for cell reaction, K0 double prime is the specific zero order rate constant and X is the cell concentration. So, now the first order reaction also we see that from the chemical point of view we can present it the Ra K on Ca, and from the Ra means dCa dt. From there we can develop the equation that the C ln Ca by Ca0 equals to K on. So, Ca equals to Ca0 K on e to the power minus K on T, but this type of equation, but in enzymatic reaction this or the microbial reaction, this also depends on the concentration of enzymes or microbes. But beyond this, Michaelis-Menten develop a enzymatic equation where the kinetic of the most enzyme reaction are follow this equation. Here R is the reaction rate, that is V max is the maximum velocity, and Ca is the concentration of the reactants. K is the Km is the Michaelis-Menten constant, and Ca is the again concentration of the reactants. So, this is basically in conventional symbols are like this, that the S is the substrate concentration. Normally in biologically system we put it as a substrate concentration. So, this is V is the volume, V is the velocity of the reaction, that means how much substrate is going to be changed per unit time, that is the Ts dt. So, if that we put in the reaction and we rearrange this reaction, so it can be written in this fashion that the 1 by Rs equals to Km by Vx into 1 by S plus 1 by V max. Now, if the data available on the substrate concentration, this few data are presented here, and the reaction rate are also based on this substrate concentration are taken based on the reaction. So, then we can use this data for calculation of the parameters, means that is the Km and V max. So, in this equation if we take the 1 by Rs, that is the reaction rate in the y axis, and 1 by S in the x axis. So, the straight line we will get, and from the slope of that we can get the Km by V max, and from the intercept 1 by V max. So, from there we can calculate the V max and Km, this the Michaelis-Menten constants. So, from this data it is calculated here, and it is observed that the Km equals to 0.0266 kilomole per meter cube, and the reaction can be presented in this fashion, that minus Rs equals to 1.33 into substrate concentration by Km value is the 0.0266 plus S. So, that is on more illustrations is given here, but in a mixed flow reactor the same as we know, this is the tau S0 minus S by Rs. So, in case of Rs we put the Michaelis-Menten equation. So, that is we can write this in this fashion, and here if we rearrange the equation in this way, the S equals to minus Km plus V max S into tau by S0 minus S. So, now if we plot this S as a y axis and S tau by S0 minus S in the x axis. So, then the intercept will be the minus Km, and from the slope we can calculate the your V max. So, this way the kinetic for the mixed flow reactor we can calculate the parameters of rate by Michaelis-Menten constant and the maximum velocity, that is V max. Similarly, for the batch and plug flow reactor where the equation V equals to minus ds by dt, in this fashion we can write it, and here T equals to minus integration of ds by minus Rs and S0 to S, and from this is the Michaelis-Menten equation if we put and if we integrate these types of equations. So, we get here you see that the in different t we can calculate what is the conversion what is the constant and the Vmax we can calculate from here and this is nothing but in different way we can present in our system in this way that the Vmax by Km equals to 1 by T ln S 0 by S in plus S 0 minus S Km into T. And so, now if we plot 1 by T the reaction time in S 0 is the initial concentration of the substrate by any time substrate concentration means T time at the T time substrate concentration is S. So, in this in the x axis and is plotted against the S 0 minus S by T, it is in the y axis, it will yield a straight line with slope minus 1 by Km and the Vmax by Km. So, from this equation by the graphical presentation we can calculate the the estimation of the kinetic parameters. So, now we will talked about the microbial fermentation, and in this case that the microbes when added into the system, the initial phase that is called the log phase, when the microbes are just adjusting with the system, and at that moment the microbes are not growing, I means there will be no cell division at this condition, but then it will start as a acceleration phase, then the mu value will be the positive, and after that the growth phase, when the most balanced phase, it is the microbes are growing very rapidly, and after that growth phase, a decline phase, when probably the some substrate availability is reducing, and so that the deceleration phase or the decline phase is observed. And in a stationary phase, in that case, when how much microbes will be grow, that much microbes is going to be die. So, that is the basically the stationary phase, the no change of microbial growth observed in this case, and the death phase where the growth is lesser than the death. So, that is the decline or the totally death phase. So, the microbes are going to die here. So, basically from the industry point of view, this growth phase is very important, and that is the maximum possibility of obtaining the product. So, this different mu conditions has been tabularized here, that the lag phase mu equals to 0 means the no growth, and the acceleration phase mu is below mu max, but growth phase mu equals to mu max, that is the maximum growth observed, and the decline phase again reducing, and the growth is stationary phase, and death phase it is the less than 0. So, now for the balanced growth means when the process parameters point of view and the substrate point of view are all favorable for the microbial growth, and then that is the most useful time for the growth of the microbes, and so that the products formation and the product harvesting is the maximum. As in this case, that the R z equals to mu z, here z is the cellular constituents such as protein, RNA, polysaccharide, etc., and R z is the volumetric rate of production, volumetric, and z is the concentration of the product, means the it may be enzyme, maybe the cell itself, maybe the polysaccharide, maybe the pigment, maybe the biodiesel, etc., etc. So, then another types of growth kinetics was developed by the Michaelis-Menten, that is mu equals to mu max S by Ks plus S. Here S is the substrate concentration and mu max is the maximum growth rate maximum growth rate, and mu is the anytime growth rate. So, this is considering only the single substrate condition exerts a dominant influence on rate of the growth. So, based on that, this equation like the for this substrate concentration, maybe the sugar concentration, maybe the any protein concentration or others. So, based on the single substrate concentration, this equation is developed. So, a tricky calculation is there. If we consider mu equals to mu max in the previous equation, we will get the substrate concentration, and that is from that equation that is nothing but the Ks value. So, different microbes have the different Ks value, and that is tabulated here, that the Ks value for Saccharomyces in when the glucose as a main substrate of growth is the 25 milligram per liter, and for the Acacia it is lactose, it is 20, and that way others microbes with their limiting substrate given in this table, and maximum it is observed at the 120, then the methanol is the limiting substrate, and hence Henula is the microorganism. So, then after inoculation, the growth rate of the cells gradually increase. So, we have mentioned, but from the product point of view, the exponential phase or log phase will be the most important and interesting one. So, in this case dx dt, which is the microbes growth rate is increasing with time, is the mu g growth of the mu g into x, minus kd is the death rate into x, but in this case normally it is considered that kd is the 0. So, from this equation we got by integration x equals to x0 e to the power mu g t. So, this is the condition where the maximum productivity can be obtained. And similar as Michaelis-Menten equation, if we want to calculate the kinetic parameters, we can take the reciprocal of 1 by mu and Ks by mu max 1 by S plus 1 by mu max. Now, if we plot 1 by mu versus 1 by S, then 1 by mu in versus 1 by S, then slope will be the Ks by mu max and intercept will be the 1 by mu max. So, from there we can calculate the kinetic parameters of these biological reactions. But in that case it was considered the single substrate, but in some cases, especially in waste management or waste treatment system, lots of substrate are available or the pollutants are available. Then in that case, though biological treatment, but then also biological treatment, we cannot use that monod equation, and then Thomas model will be the better one as a multi-component as a substrate. So, then the equation is like this: T by y, y is the remaining waste concentration, and LU is the maximum waste concentration, and K1 prime is the rate constant, and T is the time of reactions. So, this equation is very widely accepted, and it is used for the calculation of the kinetic parameters. At the same time, that the temperature variation also increase the thermal increase the rate constant, and that is K1 prime T is at a base temperature. If we consider to 4 to 20 degrees centigrade, then theta value to the power T minus T0 or in this way we can define the equation, and but it is observed that the temperature range in a very narrow range only possible for this reaction for any specific type of organism. Otherwise, it will beyond that the microbes cannot sustain the temperature or cannot be activated in the very lower temperature. So, it can go in the dormant state. So, it cannot work well, or in higher temperature it can be totally destroyed due to the thermal shock. So, these equations will be valid only the narrow range of the optimum temperature which grow the microbes very well growth is observed. So, here some data we have presented by the waste treatment system. Here using the Thomas equation, here plot is the T by y to the power 1 by 3 and the time is the days, and this is the plot. So, from there we have calculated intercept, and intercept is the this portion is the intercept, and this is this part is the slope. So, from there two unknown, that the k on prime LU and k on both can be calculated, and it was calculated, and the kinetic parameters it comes like the 0.085. So, that was the microbial point of view, and then it is another types of kinetics is the Hill kinetics. In Hill equation is an equation used in biological biochemical characterization. In biochemistry, it has observed that the ligand to a macromolecule whenever some substrate is binding to an enzyme, and then that enzyme is getting activated to or the more active to bind the another substrate. That means at a time that the one enzyme can bind more than one substrate. But in Michaelis-Menten, this was considered that one substrate at a time can bind only one ligand, I mean one enzyme, one substrate. But here one enzyme more than one substrate can bind. So, this equation Hill developed the equation in this way: V by V max s to the power n k 0.5 plus s to the power n. So, this is nothing but this equation was can be presented in this fashion, where and from the experimental data we can calculate the n value and k 0.5 values, etc. So, for that we have to plot the experimental data here, log s and log v by v max minus b. So, from there we can calculate the kinetic parameters, and n value, it is observed that as the n different n value, the plot of the curve is different, and it indicates that the all curves are sigmoidal in nature. So, and this n value is called the cooperativity. This is nothing but as the n value is n equals to 1, 2, 3 and 4, different types of diagram has been plotted here, and each curve represent a different Hill coefficient. A vertical axis displays a fraction of theta that occupied ligand binding sites on the protein receptor equal to the ratio of the concentration of ligand bound protein to the total concentration of the protein receptor. The horizontal axis is the ratio of the ligand concentration producing the half occupation of the total ligand concentration. So, this nothing but these types of curve when we are presenting. So, the sigmoidal nature, it means the enzymes are showing the cooperativity, highest cooperativity, and that is the nature of curve which only be will only be calculated the proper kinetic parameters from the Hill equation, and if we plot it into the Michaelis-Menten equation, that the kinetic parameters will not be the accurate on, and so different parameters will be calculated and from the Hill equation only. Thank you.